Welcome. In this session, we'll explore polynomial approximations to a function. In a previous session, we had a dynamical system, and the dynamical system was oscillating and decaying. And what we wanted to do was numerically estimate that first minimizer for the t being greater than 0, t being the scalar argument. And to do this, we may not have that function available to us. That is, it may be only through a numerical call. And so we can't, for example, differentiate that function and set the derivative to 0 to find the stationary points. So instead, what we'll do is we'll locally approximate it. And in doing so, what we'll do is we'll say that what we're given is a function that has a scalar argument, and we might write that in a different form as a map from a real number to a real number. And in this course, we'll interchange between these. What we'll do is we'll use an approximation, and that approximation we'll use polynomials, so we'll write that as a polynomial that has a scalar argument. And now we can say, well, what possible polynomials are there? The first thing we might consider is a 0th order approximation. And in that, what we're saying is the polynomial, and some sources will put a subscript 0 to indicate that there's a 0th order of t, and that would just be some level. That is, no matter what the argument is, this polynomial evaluates to a level. And graphically, what that would look like is if the horizontal axis is our argument t, and the vertical axis is the response, this would be a constant line. And because it's a constant line, everywhere is a minimizer and nowhere is a strict minimizer. And that doesn't look like it's going to be useful in this application. The next thing we might consider is we might consider a first order. And a first order polynomial would be, we want to approximate this as, and if we were using MATLAB, we would do one thing. What we'll say is that this might be some multiple of the scalar plus some offset. And so this would be a linear function. What that would look like is if the horizontal axis is our argument and the vertical axis is our response, this will be some line. And again, this doesn't look like it's particularly useful to us in this context, because this goes to negative infinity and there is no finite number that is a minimizer or a strict minimizer of that approximation. The next thing we could try is a second order. And that would be a polynomial, and some sources will strictly put the order as a subscript, and in MATLAB notation, that would be a first coefficient times the square of the argument plus a second coefficient times the argument plus a third coefficient. If we were to graph this, again, the horizontal axis is our scalar argument and the vertical axis is the function's value, this would look like a parabola, and it would go off to positive infinity. In this case, we want this to be convex, and by convex we mean it's pointing upward. And now the stationary point will be where the first derivative of this is exactly equal to 0, and there will be 1, and that will be here. And so what we could do is we could find this as the global minimizer of our polynomial approximation. So the question that this raises is, how do we compute a polynomial approximation to a function? And in particular, how do we compute a second order polynomial or a quadratic approximation to a function? And that will be a subject for later sessions.